Imagine holding the entire observable universe in your hands. Every star, every planet, every ocean, every atom that has ever made up a living thing, and being told that you are holding less than 5% of what exists, that the rest is something else entirely. Now imagine that even within that 5%, the ordinary matter, the stuff you are made of, more than 3/4 of it has, for most of modern science's history, simply been missing, not theoretically absent, not philosophically uncertain, empirically unaccounted for gone. Where does matter go when it vanishes from the places where matter is supposed to live? Why does the universe, which emerged from a fireball of staggering density, arrange itself into structures so hauntingly, so almost philosophically empty? And why, after decades of searching with the most powerful telescopes ever constructed, did the answer turn out to be hiding in plain sight, stretched across invisible threads between the galaxies, too hot to see, too thin to touch, too vast to have ever been measured before a new class of cosmic flashlight finally illuminated it? There is a census of the universe. It is not conducted by any single agency, or from any single telescope, or even in any single century. It is a slow accumulation of evidence gathered across decades of careful, painstaking measurement of light collected from objects billions of light years away, of ancient radiation preserved from the first few 100,000 years of cosmic existence, of the chemical fingerprints burned into the very first atoms forged in the fires of the Big Bang itself. And what that census tells us, with a precision that should be unsettling, is that we have been looking at the universe wrong. The standard model of cosmology, the framework known as lambda CDM, which has survived every major observational test thrown at it for half a century, describes a universe whose total mass energy budget is divided into 3 unequal portions. Dark energy, the mysterious repulsive force driving the accelerating expansion of space, accounts for approximately 68.2% of everything. Dark matter, the invisible gravitational scaffolding around which all visible structure assembled itself, accounts for a further 26.8%. And ordinary matter, baryonic matter, the protons and neutrons and electrons that make up stars, planets, gas clouds, human beings, everything we have ever touched or measured or seen, accounts for the remaining 4.8%. That 4.8% is the universe we live in. Every galaxy ever photographed, every nebula, every ocean, every mountain range, every cell of every organism that has ever drawn breath on this or any other world. That is 4.8% of what exists. But here is where the ledger begins to fracture. When cosmologists set out to actually count all the ordinary matter they can observe in the present-day universe, the stars in galaxies, the cold gas between stars, the hot gas in galaxy clusters, the dust, the planets, everything accessible to a telescope, they come up dramatically short. Not by a rounding error, not by a measurement uncertainty that could be dismissed. For most of the 20th century, the observable census of baryonic matter in the local universe accounted for less than half of what the early universe should have bequeathed it. This is the missing baryon problem, and I want to be precise about what makes it so destabilizing as a scientific mystery, because precision here is everything. The total quantity of ordinary matter in the early universe is not a guess. It is determined by 2 entirely independent measurements, both of which agree with each other to extraordinary precision. The first comes from Big Bang nucleosynthesis, the nuclear physics of the first 20 minutes after the Big Bang, when the universe was hot and dense enough to fuse hydrogen into helium and helium into trace quantities of lithium and deuterium. The ratios in which those elements were produced depend sensitively on how many baryons were present at the time of fusion. By measuring those ratios in the most pristine, chemically uncontaminated regions of the universe today, cosmologists can work backwards and calculate the baryon density of the primordial universe with remarkable accuracy. The second measurement comes from the cosmic microwave background, the afterglow of the Big Bang itself, the faint residual radiation that fills every corner of the observable universe at a temperature of 2.725 Kelvin. Embedded within the slight temperature variations of this radiation, the CMB anisotropies, first mapped in precise detail by NASA's COBE satellite, and later refined with extraordinary resolution by ESA's Planck spacecraft, is a record of acoustic oscillation, pressure waves that rippled through the hot plasma of the early universe and froze their pattern into the microwave sky. The second peak of the CMB power spectrum is particularly sensitive to the baryon density. The Planck 2018 data nailed the baryon density to a precision of better than 0.5%. Egbert 0.0224 plus 0.00001. Baryons constitute 4.8% of the universe's total energy content. Full stop. So the early universe left us a receipt. A precise, independently verified, multiply cross-checked receipt. And when modern astronomy tried to match that receipt against everything it could observe in the present-day universe, it found that somewhere between 30% and 50% of the order had never arrived. The stars in all galaxies combined contain roughly 7% of the total baryonic budget. Cold gas in galaxies, the interstellar medium, the fuel for future star formation, adds perhaps another few percent. Galaxy clusters, those massive congregations of hundreds to thousands of galaxies bound together by gravity, contain hot X-ray emitting gas that adds a further several percent. The circumgalactic medium, the diffuse haze of gas surrounding individual galaxies, extending out to several hundred kiloparsecs from a galaxy's centre, contributes perhaps 5% more. Add it all up with meticulous care, and you arrive at something in the range of 60% to 70% of the baryons the universe is supposed to contain. The rest, hundreds of billions of times the mass of our sun's worth of matter, across every observable region of the cosmos, was for decades simply unaccounted for, not missing in the sense that it had been destroyed. Matter cannot be created or destroyed on cosmological scales. Missing in the sense that it existed in a form, at a temperature, at a density so extreme, so counterintuitive, that every telescope ever built before the 21st century was effectively blind to it. The universe had hidden its own matter in a form that looked, to all our instruments, like nothing at all. But before we can understand where it went and why, we need to understand the shape of the universe, the architecture into which all this matter was supposed to settle, the great cosmic web that gravity wove from the primordial quantum noise of the Big Bang, because the architecture is not what you might expect. And the emptiness within it is not accidental, it is in a sense the point. Take every galaxy in the observable universe. Somewhere in the range of 2 trillion of them, according to a 2016 count that revised earlier estimates upward by a factor of 10, and ask where they live. Not which galaxy, and not which group or cluster or supercluster. Ask instead what fraction of the observable universe's volume they actually occupy. What fraction of the total space is filled with the luminous structures we call galaxies? The answer is a number so small it borders on the philosophically disorienting. Galaxies, including their surrounding dark matter halos and circumgalactic gas, occupy something on the order of a few tenths of 1% of the total volume of the observable universe. The rest, more than 99% of all the space that exists within the horizon of our observations, is occupied by cosmic voids. Cosmic voids are not merely gaps. They are not the spaces between things the way a room is a space between walls. They are the dominant structural feature of the universe. They are what the universe mostly is. Their typical diameter ranges from 30 to 300 million light-years, and the matter density within them is less than 1/10 of the cosmic average. Some voids contain a handful of sparse, isolated galaxies. The largest known contain effectively nothing at all. The most arresting example lies in the direction of the constellation Bootis, first identified in 1981 by a team led by Robert Kirshner at the Harvard-Smithsonian Center for Astrophysics. At the time, the discovery was so unexpected they initially assumed a data error. The Boots void spans approximately 330 million light-years in diameter. Within it, astronomers have identified only around 60 galaxies. If our own galaxy were located at the center of the Bootis void, we would have had no evidence whatsoever for the existence of other galaxies until the invention of modern redshift surveys. For most of human history, our night sky would have been, in the strictest sense, empty of anything beyond our own stellar neighbourhood. The Milky Way itself resides within a somewhat more modest underdense region called the KBC void, which spans roughly 2 billion light-years across and is centred on our local neighbourhood of space. Voids are not random. They are the photographic negative of the cosmic web, the intricate, foam-like structure of filaments and nodes and sheets and walls that traces the large-scale distribution of matter in the universe, and which represents the single largest organised structure in existence. The cosmic web emerged from the quantum fluctuations of inflation, microscopic variations in energy density that were stretched to cosmic scales in the first fractions of a second after the Big Bang, imprinting a faint pattern of overdensities and underdensities across all of space. Gravity then did what gravity always does. It amplified the overdensities and evacuated the underdensities. Regions that were fractionally denser than average pulled matter inward. Regions that were fractionally emptier became emptier still. Over billions of years, this process sculpted the universe into a three-dimensional architecture that cosmologists have compared, with good reason, to a cosmic sponge, a foam of soap bubbles, a spider's web of extraordinary and terrible beauty along the filaments, the elongated strands of the cosmic web, stretching for tens to hundreds of millions of light years. Matter accumulated. At the intersections of filaments, where multiple strands crossed and merged, the densities grew high enough to form galaxy clusters, the most massive gravitationally bound structures in the universe. Galaxies formed preferentially within the dark matter halos that populated the filaments and nodes, and the voids expanded, growing emptier as the filaments drained them of their contents, until the universe arrived at its present state. A foam of nothingness held apart by glowing threads, with the entirety of visible civilization clustered along the seams. But here is the complication, and it is a complication that took decades to fully appreciate. The filaments, for all their structural grandeur, do not contain most of the baryons. Galaxies, which are the brightest and most visible concentrations of ordinary matter in the universe, do not contain most of the baryons either. Galaxy clusters, which astronomers long considered the most matter-rich environments in the cosmos, contain only about 4% of the total baryon budget in their hot intracluster gas. The circumgalactic medium adds another 5%. Stars and cold galactic gas together contribute perhaps 10% more. You are already at 19%, and you have described every bright and observable structure in the universe. Where is the remaining 81%? This is the question that consumed cosmologists for the better part of 3 decades. The answer, when it began to reveal itself, required understanding not just where matter was, but what had been done to it. What physical processes had transformed it into something so diffuse, so hot, so utterly transparent to the wavelengths of light astronomers had spent their careers studying that it had vanished from view entirely. It required understanding a process that is, when you sit with it, one of the most dramatic and violent sequences of events in the history of the cosmos, the systematic expulsion of matter from the very galaxies that were supposed to contain it. But before we get to the mechanism of that expulsion, before we understand the cosmic thermostat that blew most of the universe's ordinary matter out into the void, we need to sit with a deeper paradox. Because the emptiness of galaxies is not just a matter of where the baryons ended up. It is also a matter of what the baryons failed to become. And that failure, that profound cosmic inefficiency in the conversion of gas to stars, is the second great mystery embedded in this story, and the one that cuts closest to questions about our own existence. This is what cosmologists call the star formation efficiency problem. And it is, to my mind, one of the most underappreciated puzzles in all of astrophysics. A puzzle that sits quietly at the foundation of everything we think we know about how galaxies work. Here is a calculation that should produce a universe nothing like ours. Take a dark matter halo of a given mass, the gravitational structure that defines the potential well into which baryons will fall. The ratio of baryons to dark matter in the universe is well constrained. For every unit of dark matter mass, the universe contains approximately 0.156 units of baryonic matter, a ratio set in the first few minutes of cosmic history and unchanged since. So, given a dark matter halo of known mass, you can predict with confidence how many when baryon should have fallen into it, been captured by its gravity, cooled, condensed, and formed stars over the 13.8 billion years since the Big Bang. You can calculate theoretically what fraction of a halo's baryonic budget should have been converted into stellar mass. The answer your theory gives you is far too high. Galaxy after galaxy after galaxy falls short of the baryon fraction its dark matter halo predicts. In a halo the mass of our own Milky Way, only about 20% of the available baryons have been converted into stars over the galaxy's entire lifetime. In smaller dwarf galaxy halos, the efficiency drops precipitously, sometimes to 1% or less. Even in the largest galaxy clusters, where conditions should be most favourable for retaining gas, the stellar mass fraction is a mere 1 to 2% of the total baryonic budget. If you took the standard cosmological baryon fraction and asked what fraction of those baryons ended up in stars across all galaxies, the answer is somewhere between 5% and 10% of the total. The universe converted at most 1 atom in 10 into a star. The other 9 went somewhere else. This is not a minor discrepancy. This is a factor of 10 shortfall between theory and observation. If all the baryons that gravity pulled into dark matter halos had simply cooled and condensed into stars, as naive models suggested they should, then the night sky would be ablaze with galaxies 10 times brighter than those we observe, each one 10 times more massive, the universe 10 times denser with stellar light. The sky would look nothing like it does. The galaxy populations we observe would be impossible. Something prevents galaxies from forming stars from most of their gas. Something heats it, or expels it, or keeps it turbulent enough that it cannot collapse. And that something has been identified, not as a single process, but as a pair of processes operating across different mass scales, like 2 regulators on a cosmic thermostat, set to prevent runaway star formation. The first process operates at the low mass end. In dwarf galaxies and small spirals, the primary mechanism is stellar feedback, the combined energetic output of the stars that do form, turned against the gas that would form the next generation. A massive star, say 125 times the mass of our Sun, lives a brief, incandescent life of perhaps 8 million years before detonating as a supernova with an energy release of approximately 1044 joules, the equivalent of what our Sun will radiate over its entire 10 billion year lifetime, unleashed in seconds. A single supernova can drive a shock wave through the surrounding interstellar medium at velocities of several thousand kilometers per second, sweeping up and heating gas over regions hundreds of light years across. In a starburst episode, when a burst of vigorous star formation ignites across a galaxy, thousands of supernovae can occur within a few million years, their combined energy outputs generating a galactic superwind, a coherent outflow of heated, enriched gas that punches through the galaxy's disk and erupts into the circumgalactic medium at velocities of several hundred to over 1,000 kilometers per second. In a small galaxy, where the escape velocity from the dark matter halo is modest, perhaps 50 to 100 kilometers per second, that outflow simply leaves. The baryons are expelled from the galaxy entirely, scattered into the circumgalactic medium, and eventually into the broader intergalactic space. This is why dwarf galaxies are so spectacularly inefficient at forming stars. Every burst of star formation partially destroys the conditions for the next burst, blowing the raw material out into the void before it can cool and condense. It is a process of violent self-regulation, and it means that small galaxies are, in a very real sense, their own worst enemies. But stellar feedback alone cannot explain the behaviour of massive galaxies, the giant ellipticals and massive spirals that anchor the largest clusters and groups. In a galaxy with an escape velocity of 600 kilometers per second, supernova winds simply cannot expel the gas. The thermal energy of even a sustained starburst is insufficient to unbind the baryons from a massive halo, and yet massive galaxies are, if anything, even more efficient at shutting down star formation than their smaller counterparts. The most massive galaxies in the universe, the enormous red elliptical galaxies that populate the dense cores of rich clusters, stopped forming stars billions of years ago and have remained largely quiescent ever since, their stellar populations aging passively, their colours reddening as the bluer, shorter-lived stars die out. Something else killed them. Something more powerful than supernovae. Something that operated at the very centre of the galaxy itself. Something that could heat and expel gas from a halo whose escape velocity was hundreds of kilometres per second, and do it repeatedly, maintaining the quenching over cosmic timescales. That something sits at the centre of every massive galaxy in the universe, and it is one of the most extreme objects that the laws of physics permit to exist. The supermassive black hole, the connection between the mass of a galaxy's central black hole and the properties of the galaxy's stellar bulge. First noted with growing alarm by astronomers in the late 1990s, is one of the most profound empirical correlations in astrophysics. The mass of a black hole sitting at the centre of a galaxy correlates with the velocity dispersion of the stars in the galaxy's bulge to a degree that indicates a deep causal relationship between two objects separated by a factor of roughly 10 billion in physical scale. The black hole at the centre of a galaxy is a billion times smaller in extent than the galaxy itself, and yet it seems to know, through some feedback mechanism, how massive the surrounding stars are. This is what astrophysicists call the M-sigma relation, and it remains one of the most compelling pieces of evidence that the growth of supermassive black holes and the formation of stars in their host galaxies are not independent processes. They are regulated by each other. They co-evolve. The mechanism operates through a process called active galactic nucleus feedback, AGN feedback, and its power output dwarfs even the massed supernova rate of the most intense starbursts. When a supermassive black hole is actively accreting infalling gas, the region immediately surrounding it, the accretion disk, radiates with a luminosity that can exceed that of the entire galaxy by factors of 10, 100, or even 1,000. This is what a quasar is, an actively feeding supermassive black hole, the accretion disk of which outshines the combined light of hundreds of billions of stars. A quasar phase AGN can drive winds outward through its host galaxy at velocities of 10,000 to 30 kilometers per second. Winds powerful enough not merely to disrupt star-forming clouds, but to physically remove gas from the galaxy altogether, blowing it out beyond the dark matter halo and into the intergalactic medium. I find the scale of this genuinely staggering to sit with. A black hole of perhaps 1 billion solar masses, occupying a region of space roughly the size of our solar system, regulates the growth of a galaxy containing hundreds of billions of stars, spread across 100,000 light-years, by periodically erupting with enough energy to expel the entire gas reservoir of that galaxy into the surrounding intergalactic medium. The black hole is, in the most literal sense, the thermostat of the galaxy. When the galaxy gets too gas-rich, the black hole feeds, erupts, and purges the fuel supply. When the galaxy's gas content falls, the black hole goes quiet, and the cycle waits to begin again. In the most massive halos, galaxy clusters hosting trillions of solar masses of dark matter, the AGN feedback takes a gentler but more persistent form. The black holes in the central brightest cluster galaxies drive powerful relativistic jets of plasma outward, into the hot intracluster medium, inflating vast cavities, radio bubbles tens to hundreds of kiloparsecs across, that heat the surrounding gas and prevent it from cooling and condensing. This is the jet mode of AGN feedback, and X-ray observations from observatories like Chandra and XMM Newton have revealed it operating in hundreds of galaxy clusters, the X-ray cavities carved by the jets, writing the history of the black hole's feeding cycles into the hot plasma around it, like rings in a tree trunk. So we now have two mechanisms, stellar feedback operating primarily in low-mass halos, AGN feedback operating primarily in massive halos, that together can account for the catastrophic inefficiency of star formation across galaxy populations. They explain why galaxies converted only about 5 to 10% of their baryons into stars. They explain why the most massive galaxies died early and remain dead. They explain the shape of the galaxy luminosity function, the bimodal colour distribution of galaxies, the existence of the red sequence, and the blue cloud that astronomers observe when they survey the colour and star formation properties of galaxies across cosmic time. But they introduce a new question, one that is in some ways more profound than the one they answer. If these feedback mechanisms expelled the gas from galaxies, if stellar winds and supernova-driven outflows and AGN-powered quasar winds blew the baryons out of the halos that captured them, then where did all that expelled gas go? What is the thermodynamic state of the matter that was ejected? Where, precisely, in the large-scale structure of the universe does it reside now? Is it observable? Can it be measured? And does it, when counted, finally close the baryon budget and reconcile the universe's present-day matter inventory with the receipt handed down by Big Bang nucleosynthesis? These are the questions that defined 3 decades of observational cosmology from the 1990s onwards, and the search for their answers constitutes one of the great detective stories of modern science. It led observers to develop entirely new detection techniques, to propose entirely new physical phenomena, and eventually, through an instrument that was never designed for the purpose, to finally weigh the invisible ocean of matter hiding between the galaxies. But the path to that solution ran first through a woman standing at a spectrograph in the cold silence of a mountaintop observatory in the 1960s and 1970s, measuring the motions of stars and galaxies that refused to behave the way they were supposed to. And understanding what she found is essential to understanding the full depth of the problem, because her discovery did not just reveal that galaxies were emptier than expected. It revealed that they were emptier than possible, unless something invisible was doing the work that ordinary matter was failing to do. By the mid-1960s, the broad outlines of galaxy dynamics were considered settled. The rotation of spiral galaxies, the rate at which stars and gas clouds orbit the galactic centre at different distances, was expected to follow a pattern that physicists called Keplerian decline, named for Johannes Kepler's laws of planetary motion. The principle was straightforward. Objects orbiting a central mass concentration should move faster when closer and slower when farther away, their orbital velocities falling off in a predictable curve as the enclosed mass becomes a smaller and smaller fraction of the total at larger radii. Our own solar system obeys this beautifully. Mercury, closest to the Sun, orbits at 47 km per second, while Neptune, 30 times farther out, crawls along at just 5.4 km per second. Galaxies were expected to behave the same way. The bulk of a galaxy's visible mass, its stars, its gas, its dust, is concentrated toward the centre. As you move outward through the disk, the enclosed mass grows more slowly, and eventually, beyond the visible edge of the galaxy, it should barely grow at all. The stars at the outer edges of a spiral galaxy should therefore be moving measurably slower than those closer in, and the rotation curve, the graph of orbital velocity plotted against radius from the galactic centre, should exhibit the characteristic declining slope that Newtonian gravity predicts. Vera Rubin had spent most of her professional life being told, in explicit and implicit terms, where she did not belong. She was told at 18 that Princeton's graduate astronomy program did not admit women. She was told, by the way her first scientific paper was received when she presented it at 22, 3 weeks after giving birth, to the American Astronomical Society, that her ideas about the non-random distribution of galaxies were premature and insufficiently supported. The Washington Post reported her presentation under the headline, "Young Mother Has Own Theory of Universe," a line that encodes in 6 words the precise texture of the condescension she would spend the next 4 decades navigating. When she applied in 1965 to observe at Palomar Observatory, the most powerful ground-based observatory in the world at the time, she became the first woman ever permitted to do so, not because the institution welcomed her, but because she simply applied and they had no written rule prohibiting it. The bathroom situation was resolved, as Carnegie president Eric Isaacs later recounted, by Rubin cutting a small paper skirt and taping it to the stick figure on the men's room door. She then got to work. By the early 1970s, Rubin was collaborating with instrument maker Kent Ford at the Carnegie Institution of Washington, using Ford's image tube spectrograph, a device that amplified the spectra of astronomical objects too faint for conventional photographic plates to systematically measure the rotation curves of spiral galaxies. She began with Andromeda, our nearest large galactic neighbour, then extended her survey to dozens of other spirals of varying sizes, orientations and distances, and what she found, galaxy after galaxy after galaxy, was not a Keplerian decline. The rotation curves were flat, not approximately flat, not flattish, within the error bars of uncertain measurements, flat in a way that was unambiguous, and once you understood its implications, deeply unsettling. Stars at the outer edges of spiral galaxies were moving at roughly the same velocity as stars near the centre. Orbital velocities of 200 to 250 kilometers per second, maintained at essentially constant levels from the inner disk out to the farthest detectable radii, with no sign of the Keplerian decline that would signal the edge of the dominant mass distribution. This could only mean one thing. The mass of the galaxy was not concentrated at the centre, as the distribution of visible light implied. The mass was distributed throughout a vast, roughly spherical halo extending far beyond the visible edge of the galaxy. A halo so large that even at the outermost detectable limits of the disk, you were still deep inside the dominant mass distribution, still experiencing its gravitational pull, still orbiting a centre that enclosed most of the mass within your radius. The enclosed mass of the galaxy was still growing at the outermost detectable radius. It kept growing into a dark, invisible halo that extended perhaps 10 times farther than the visible stars. And that halo, by definition, contained nothing that emitted light. When Rubin published her comprehensive rotation curve survey in 1980, covering 21 spiral galaxies, all showing the same flat behaviour, the conclusion was, as she wrote, inescapable. There was vastly more mass in spiral galaxies than the visible stars and gas could account for. Her calculations showed that galaxies must contain at least 5 to 10 times more mass than could be observed directly. The matter we can see, everything that emits, reflects, or absorbs electromagnetic radiation, is a minor constituent of a galaxy's total mass, floating within a much larger and much more massive dark halo, whose nature was entirely unknown. Rubin had not discovered dark matter in the sense of identifying what it was. Fritz Zwicky had inferred its existence from galaxy cluster dynamics in 1933, and Rubin herself was careful to note that she was not ruling out alternative gravitational theories. She provided something Zwicky had never been able to, a systematic, statistically overwhelming, methodologically unimpeachable body of observational evidence that the discrepancy between visible mass and dynamical mass was universal, consistent, and enormous. Every spiral galaxy she measured told the same story. The universe was full of mass that nobody could see, and the ordinary matter, the baryonic matter, the atoms, was a minority player in a gravitational drama being orchestrated by something else entirely. This had a second, less immediately appreciated consequence for our story. If the dark matter halos around galaxies extended far beyond the visible stars, and if the baryons that fell into those halos had initially been distributed throughout the halo's volume, rather than concentrated in a central disk, then the question of where the baryons were became more complex and more interesting than a simple comparison of observed stars to predicted gas fractions. The baryons were not just underrepresented in stars, they were distributed differently than the dark matter. They had been processed, heated, and redistributed by the very act of galaxy formation, and much of that redistribution had pushed them outward, away from the luminous disk, into the outer halo and beyond, into the vast warm envelope of gas that surrounded the galaxy, and ultimately into the filaments and voids of the cosmic web. What Rubin's flat rotation curves told us, ultimately, was not merely that galaxies are heavier than they look. They told us that the baryonic component of a galaxy, the ordinary matter we can in principle see and measure, is a minority fraction of a much larger structure, hosted by a dark matter halo that is itself just one node in the vast and mostly empty cosmic web. The matter problem, in other words, was not separate from the emptiness problem. They were the same problem viewed from opposite directions. The galaxies were emptier than expected because the ordinary matter had been expelled from them, and the ordinary matter had been expelled because the very process of building galaxies was violent enough to undo, repeatedly and efficiently, much of what gravity had assembled. Rubin's contribution was to make the scale of the problem undeniable. Before her systematic survey, the mass discrepancy in galaxies could be attributed to measurement uncertainties, unusual objects, or optimistic assumptions about missing stellar mass. After 21 galaxies, all showing the same flat curves, that comfort was no longer available. The universe was not built the way anyone had assumed, and the missing baryons were not a theoretical curiosity. They were the dominant form of ordinary matter in the cosmos, drifting, invisible, unaccounted for, in the vast spaces between the luminous structures that had always defined our map of the universe. She spent the rest of her life working at her spectrograph and advocating for the women who came after her. She measured more than 200 galaxies in total. She was, by any measure, the person who placed the missing baryon problem on an observational foundation solid enough to demand a solution. She died on Christmas Day, 2016, at age 88. She never received the Nobel Prize. The Nobel Committee's rules prohibit posthumous awards, so the question of whether that oversight will ever be corrected is now permanently closed. It remains, to my mind, one of the most consequential failures of recognition in the history of science. But the problem she illuminated did not go unresolved. The solution, when it came, arrived from a direction that almost no one anticipated, and it required confronting not just where the baryons were, but what extreme physical state they had been driven into by the violence of the cosmic thermostat. By the mid-1990s, a theoretical prediction had crystallized from computer simulations of cosmic structure formation that was, if correct, simultaneously the most elegant and the most frustrating possible answer to the missing baryon problem. The baryons were not in galaxies. They were not in galaxy clusters. They were not in the cold gas of intergalactic space. They were in the filaments of the cosmic web, threaded along those vast, tenuous strands of matter connecting galaxy clusters across hundreds of millions of light years, but in a physical state so extreme that conventional astronomical observations were essentially blind to them. The simulations, growing in sophistication through the 1990s and into the 2000s, as computational power allowed increasingly detailed modelling of both dark matter dynamics and baryonic physics, painted a consistent picture. The matter that had been expelled from galaxies by stellar feedback and AGN outflows, along with the primordial gas that had never been dense enough to fall into dark matter halos in the first place, had been heated, compressed into the filaments by large-scale gravitational flows, and driven into a temperature regime of between 105 and 107 Kelvin, hotter than the surface of any star, but cooler than the X-ray emitting intracluster gas in rich clusters. This temperature range, a vast thermal middle ground between the cold intergalactic hydrogen that could be detected in absorption and the hot cluster plasma detectable in X-rays, was given its own name by the theorists who predicted it: the warm-hot intergalactic medium. The WIM. The WIM is not a thing you can photograph. At its predicted temperatures and densities, with matter densities in the range of 1 to 10 particles per cubic meter, spread across filaments that are vast in extent but microscopically thin in cross-section, it emits almost no X-ray radiation. It emits almost no optical radiation. It is, for practical purposes, completely transparent to the wavelengths of light that ground-based and most space-based telescopes operate in. The simulations predicted that it contained approximately 30 to 50% of all the baryons in the present-day universe, and detecting it required observing from space in the extreme ultraviolet and soft X-ray portions of the electromagnetic spectrum, with instruments of extraordinary sensitivity looking for the faint spectroscopic signatures of highly ionized oxygen atoms, oxygen stripped of 6, 7, or even 8 of its electrons by the extreme temperatures, imprinted as absorption lines in the spectra of background quasars shining through the filaments. This was a technically demanding observation in an understatement so severe it verges on comedy. The oxygen absorption lines in question, the OVI, OVI and OVRE lines, lying at ultraviolet and soft X-ray wavelengths, were predicted to be extraordinarily faint, requiring telescope collecting areas and spectral resolutions that were, for most of the 1990s, beyond the reach of any operating space observatory. Ground-based telescopes could not observe them at all. The Earth's atmosphere is opaque to the relevant wavelengths, and even in space, the combination of faint signal and difficult spectral regime made detection a challenge that consumed more than 2 decades of effort, frustration, and incremental progress. First convincing detections of WIMP filaments began to accumulate in the late 2000s and early 2010s, as the Chandra X-ray Observatory and the XMM Newton Observatory, both launched in 1999, began to build up the deep, high-resolution X-ray spectra of bright background quasars needed to search for the faint absorption signatures. In 2012, a landmark paper led by Michael Schull at the University of Colorado performed a comprehensive census of baryons in the multi-phase intergalactic medium using data from the Far Ultraviolet Spectroscopic Explorer and the Hubble Space Telescope's Cosmic Origin Spectrograph, concluding that even after accounting for all identified baryonic components, including the warm WIMP phase detectable via OVI absorption, approximately 30% of the total baryon budget remained unaccounted for. The warm phase of the WIMP, detectable in ultraviolet, was found. The hot phase, detectable only in X-rays, remained elusive. Then, in June 2018, a team led by Fabrizio Nicastro of the Harvard-Smithsonian Center for Astrophysics and the INAF Observatory of Rome published a paper in the journal Nature that represented, for many in the field, the closest thing to a resolution of the missing baryon problem that had yet been achieved. Nicastro's team had used the XMM Newton Observatory to observe the quasar 1ES 1553+13, a blazar located approximately 4 billion light-years away through its soft X-ray spectrum with enough sensitivity to detect the OVII absorption signature, the hallmark of hot WIMP at temperatures around 106 Kelvin, in 2 separate intergalactic filaments along the line of sight. The detection required stacking months of XMM Newton observations, extracting a signal so faint that the team independently verified it multiple times before publication. But it was there. The hot WIMP, hiding in the intergalactic void at a density of just a few particles per cubic meter, had finally left a mark on a spectrum. Simultaneously, 2 independent teams, one led by Hideki Tanimura, another by Anna de Graaf, used the Planck satellite's all-sky maps and the thermal Sunyaev-Zeldovich effect to detect the warm intergalactic gas directly between pairs of luminous red galaxies, stacking the Planck signal from millions of galaxy pairs to beat down the noise and reveal the faint shadow cast by the intervening gas on the cosmic microwave background. Sunyaev-Zeldovich effect, in which hot electrons in ionized gas scatter CMB photons and leave a distortion in the microwave background, provided an independent handle on the total pressure of the gas, regardless of its optical properties. Their detections placed the density of gas in intergalactic filaments at approximately 30% of the cosmological critical density, precisely the fraction needed to close the gap in the baryon census. But perhaps the most decisive and comprehensive resolution came from a technique no one in the 1990s could have anticipated using for this purpose. Fast radio bursts, FRBs, the brief, brilliant millisecond flashes of radio waves that first appeared in archival pulsar data in 2007, and whose origin remained mysterious for a decade, turn out to be extraordinarily precise rulers for measuring the density of electrons in the intergalactic medium along any line of sight. A radio pulse, as it propagates through ionized plasma, is dispersed. Higher frequency components of the signal travel slightly faster than lower frequency components, arriving at the telescope a measurable fraction of a second earlier. The amount of this dispersion, quantified as the dispersion measure, is directly proportional to the column density of free electrons along the path between the source and the observer. An FRB originating at a known cosmological distance provides in effect a direct weighing of all the ionized gas between its source and our telescope. In June 2025, a team led by Dr. Liam Connor at the Harvard-Smithsonian Center for Astrophysics published in Nature Astronomy the most comprehensive FRB-based baryon census yet attempted, analysing 60 FRBs spanning distances from 74 million light-years to 9.1 billion light-years, the most distant FRB yet detected at redshift 1.5. The analysis was unambiguous. Approximately 76% of all baryonic matter in the universe resides in the intergalactic medium, in the diffuse, hot gas of cosmic filaments and the spaces between them. About 15% lives in the circumgalactic medium surrounding individual galaxies. Stars and cold galactic gas together account for only a small fraction of the remainder. The missing baryons had been found, not in galaxies, not in galaxy clusters. In the void between them, in a warm, thin, hot, nearly invisible ocean of ionized gas stretching between the filaments of the cosmic web, heated to temperatures where it could not easily be seen, maintained at densities so low that 1 cubic meter of space contained fewer atoms than exist in a grain of sand. The universe had always kept its inventory. It had simply been keeping it in a format we could not read. To understand why the baryons ended up there, why 76% of all ordinary matter in the universe is floating in the vast spaces between galaxies rather than condensed into the stars and planets of the luminous structures we can see, you need to understand the timeline. Not the timeline of individual galaxies, but the timeline of the entire baryonic universe. From the moment the first structures began to form to the present day, a history of repeated expulsion, cycling, heating, and redistribution that constitutes the most sustained and large-scale process of matter transport that physics allows. In the beginning, or rather, in the first few 100 million years after the Big Bang, once the universe had expanded and cooled enough for neutral hydrogen to form, once the epoch of recombination had passed and the CMB had decoupled from matter, the intergalactic medium was cold, primarily neutral hydrogen and helium, at temperatures of only a few hundred Kelvin, filling the universe roughly uniformly, except for the faint density perturbations that would, over time, grow into the cosmic web. Dark matter halos were assembling from those perturbations, and baryons were beginning to fall into the potential wells the halos created. Then the first stars ignited. These were monsters, perhaps hundreds of times more massive than our Sun, burning so hot and so briefly that their surfaces radiated primarily in the ultraviolet. Their ultraviolet photons streamed out into the surrounding intergalactic medium and began to ionize the neutral hydrogen, reionizing the universe, converting the neutral, dark intergalactic medium back into the ionized plasma it had been before recombination, but now at temperatures approximately 104 Kelvin rather than the thousands of degrees it had been before. This process, the epoch of reionization, stretched from approximately 400 million to 1 billion years after the Big Bang and fundamentally transformed the thermodynamic state of the intergalactic medium. What had been cold and dark became warm and transparent. The baryons in the IGM were heated to temperatures at which they could no longer easily cool and fall into the smallest dark matter halos. The thermal pressure of the warm gas competed with the gravitational pull of halos below a critical mass, preventing baryons from condensing into the smallest structures and reducing the efficiency of small galaxy formation across the board. Reionization alone, however, was not sufficient to account for the present-day distribution of baryons. The thermal energy injected by reionization could account for suppressing accretion into small halos, but it dissipated over time and the baryons it heated were not expelled from the cosmic web itself. They remained in the filaments and sheets of the large-scale structure. Something else was needed to heat the intergalactic medium to the temperatures of the WM, the 105 to 107 Kelvin range, and to maintain those temperatures against radiative cooling over billions of years. The answer, again, is feedback. But feedback operating not just within individual galaxies but across cosmic scales, the accumulated energy output of billions of galaxies over billions of years, dumped into the intergalactic medium through stellar winds, supernova-driven outflows, and AGN-powered quasar winds, heating the surrounding gas and enriching it with heavy elements in the process. The scale of this energy injection is almost impossible to internalize, but let us try. A single quasar, an actively accreting supermassive black hole, can radiate at a luminosity exceeding 1047 ergs per second, brighter than 10,000 Milky Way galaxies. If even a few percent of that radiative energy is deposited as mechanical energy in the surrounding gas, through radiation pressure, thermal coupling, or the kinetic energy of the winds and jets, then a single quasar episode can inject more energy into the interstellar and circumgalactic medium of its host galaxy than that galaxy's entire population of stars could produce over their combined lifetimes. Over cosmic time, the universe has hosted an enormous number of quasar episodes, particularly at the cosmic noon of quasar activity around redshift 2, approximately 3 billion years after the Big Bang, when the supermassive black hole population was growing most rapidly and AGN luminosities were at their peak. The gas expelled in these outflows travelled not merely into the circumgalactic medium surrounding the host galaxy, but, in the most energetic events, out beyond the dark matter halo entirely, into the intergalactic medium where it was shock heated to WM temperatures and became part of the diffuse, warm, tenuous ocean that now holds 76% of the universe's baryons. The filaments of the cosmic web were not simply passive conduits through which matter flowed toward galaxies. They were, and remain, the gravitational channels through which AGN-driven winds and supernova outflows dispersed baryons across cog scales, heating them as they went, creating the warm-hot intergalactic medium that accounts for most of ordinary matter in the present-day universe. There is a phrase that Dr. Liam Connor used in the 2025 Nature Astronomy paper that has lodged itself in my thinking since I first read it: a cosmic thermostat. The idea that supermassive black holes and supernova-driven winds operate as a thermostat, one that senses when a galaxy or its surrounding gas is too cold and dense, too close to the conditions needed for runaway star formation, and releases energy to heat and disperse it, maintaining the universe's ordinary matter in a state of carefully regulated warmth and diffuseness, rather than the cold density needed to form stars. This thermostat operates not just on individual galaxies, but on the intergalactic medium itself, cycling baryons in and out of dark matter halos, alternately cooling them through radiative losses, and reheating them through feedback events, over timescales of billions of years. The consequence of this thermostat, the consequence of this sustained, enormous, multi-billion-year process of matter redistribution, is the universe we observe. A universe in which galaxies are embedded in halos of invisible dark matter, surrounded by halos of warm, diffuse gas, connected by filaments of heated baryons, all floating in the vast emptiness of cosmic voids. A universe in which the stars and galaxies that define our visual impression of the cosmos are a startlingly, humblingly minor, component of the ordinary matter budget. A universe in which 76% of the atoms that came out of the Big Bang are drifting, invisible and unreachable, in the vast intergalactic spaces between the only structures we have ever known to contain life. But here is the question that the thermostat metaphor does not answer, and that, I think, is the deepest question embedded in this entire subject. Was the thermostat tuned? Was the balance between star formation and feedback that produced the universe we observe, the particular efficiency of 5–10%, the particular temperature range of the WIM, the particular distribution of matter between galaxies and the intergalactic void, inevitable? Or was it contingent? Could it have been different? And if it had been, would the universe be capable of producing the structured complexity, the chemistry, the planetary environments, the long sequences of cause and effect required for anything to look up at the night sky and ask where all the matter went? This is where the missing baryon problem stops being a bookkeeping question and becomes something much more profound. It becomes a question about the conditions necessary for the existence of observers, and that in turn raises the possibility that we have not yet fully understood why the emptiness of galaxies takes the specific form it does. Science has a habit of offering solutions that, upon closer inspection, reveal new problems nested inside them. The resolution of the missing baryon problem through the identification of the him as the primary repository of the universe's ordinary matter is a genuine triumph of observational cosmology. But it is not the end of the story. Several complications remain that prevent us from declaring the ledger fully closed, and understanding them requires descending from the elegance of the big picture into the messy, unresolved details of actual measurement. The first complication is detection completeness. The FRB-based baryon census of 2025, for all its power, relies on the dispersion measure as a proxy for the total electron column density along the line of sight. Free electrons are produced primarily by ionized hydrogen and helium, which are the dominant components of the JOIM. But the dispersion measure does not distinguish between electrons in different thermal phases of the intergalactic medium. It integrates all free electrons along the path, regardless of whether they are in warm WIM filaments, hot cluster gas, or the circumgalactic halos of intervening galaxies. The decomposition of the total dispersion measure into contributions from different physical environments requires modelling assumptions about the distribution of gas in dark matter halos, density profiles of circumgalactic media, and the baryon fraction of intervening galaxy clusters. These assumptions introduce systematic uncertainties that are, as the authors of the 2025 paper acknowledge, not yet fully characterized. The 76% figure for the IgM baryon fraction is the best current measurement, but it carries with it a set of modelling dependencies that require independent verification. The second complication is the baryon cycle, the continuous exchange of matter between galaxies and their surrounding circumgalactic and intergalactic environments. Baryons are not static. They flow into galaxies from the cosmic web through cold streams and filamentary accretion, are processed into stars, are enriched by stellar nucleosynthesis, are expelled back into the circumgalactic medium by feedback, cool and reaccrete, are re-expelled, cycle through multiple episodes of inflow and outflow over cosmic time. The present-day distribution of 76% IgM, 15% CGM, and the remainder in stars and cold gas is not a fixed equilibrium. It is a snapshot of an ongoing process. The rate at which matter is currently flowing between these reservoirs, the accretion rate onto galaxies, the outflow rate driven by ongoing feedback, determines how this distribution will evolve over the next several billion years. We do not yet have a complete, observationally constrained picture of the baryon cycle across all galaxy masses and cosmic epochs. The third complication is the CGM accounting, the circumgalactic medium, the extended gaseous halos surrounding individual galaxies, extending to radii of 200 to 300 kiloparsecs and beyond, has emerged as a critically important reservoir of baryons, accounting for the 15% of the baryon budget in the 2025 FRB census. But the CGM itself is a multi-phase environment of extraordinary complexity. It contains cold molecular clouds at temperatures of tens of Kelvin, warm photoionized gas at 104 Kelvin, warm hot gas at 105 to 106 Kelvin, and hot gas at temperatures above 106 Kelvin, all coexisting in a turbulent, magnetized, partially mixed environment that defies simple characterization. The mass of the CGM as a function of galactic properties, mass, star formation rate, AGN activity, environment, is still not well constrained across the full range of galaxy populations. Observations with the Cosmic Origins spectrograph on the Hubble Space Telescope and with the growing archive of X-ray spectroscopy from Chandra and XMM Newton, have mapped the CGM of relatively nearby galaxies, but the CGM of the general galaxy population at higher redshifts, where most of the galaxy evolution we care about took place, remains poorly characterized. The fourth complication, and in many ways the most theoretically interesting, is what the James Webb Space Telescope has been telling us about galaxy formation in the early universe. Beginning in 2022, JWST's infrared sensitivity and spatial resolution began revealing a population of massive, luminous galaxies at redshifts between 6 and 12, corresponding to epochs less than 1 billion years after the Big Bang, that are far more massive and far more luminous than the standard lambda CDM model of galaxy formation predicted should exist so early. Some of these galaxies appear to contain stellar masses comparable to that of the Milky Way, assembled in a universe only 300 to 500 million years old. This implies star formation efficiencies in the early universe dramatically higher than those inferred from observations of galaxies at lower redshifts. Efficiencies approaching 100% in some estimates, where essentially all available baryons in a dark matter halo were converted into stars with no feedback-driven expulsion. If this is correct, and the observations are still being interpreted, with several alternative explanations under active debate, including the possibility that the apparent stellar masses are overestimated because of unusual initial mass functions or non-stellar light contributions, then it suggests that the feedback processes that regulate star formation at lower redshifts were either absent or dramatically less efficient in the earliest galaxies. This would have consequences for the baryon budget at high redshift. If early galaxies converted their baryons into stars with high efficiency rather than expelling them into the IGM, then the WIM was not always the dominant baryon reservoir. The present-day distribution emerged over cosmic time, sculpted by the history of feedback, and the early universe may have had a very different baryon accounting that was only gradually transformed into what we observe today. The fifth complication, and I think this one deserves to be stated plainly, because it is sometimes glossed over in the triumphalist framing of the missing baryon problem being solved, is that the detection of the WIM remains observationally challenging, and the evidence for it as a specific physical entity distinct from the general warm intergalactic medium is still being assembled. The 2018 Nicastro et al. Nature detection of OVI absorption in two filaments along the line of sight to the Blazar 1ES 453 plus 113 was a landmark result, but it was based on XMM Newton observations that pushed the instrument to its limits, and replication with independent sightlines and instruments has been a slow process. The Sunyaev-Zeldovich detections by Tanimura et al. And de Graaf et al. In 2017 were statistically compelling at the 4-5 sigma level, but they were stacking analyses, measuring the average signal from millions of galaxy pairs rather than detections of individual WIM filaments. Individual filament detections in the Sunyaev-Zeldovich effect remain rare and require long observations with current generation CMB experiments such as the Atacama Cosmology Telescope. The future resolution of these complications lies with a set of facilities that are either recently completed, currently operational, or under development, and whose capabilities will transform our ability to map the warm-hot intergalactic medium with the precision the problem demands. The Vera C. Rubin Observatory, named for the woman who made the mass discrepancy of galaxies impossible to ignore, now operational on Cerro Pachon in Chile as of early 2025, will survey the sky with unprecedented depth and cadence over a decade, producing the largest and most precise map of galaxy large-scale structure ever assembled. The Euclid Space Telescope, launched in July 2023 by ESA, will map the large-scale structure of the universe across enormous volumes using the angular positions and shapes of billions of galaxies, providing constraints on the distribution of matter, both dark and baryonic, that will anchor the theoretical models of the cosmic web and allow more precise predictions of WIM properties to be tested observationally. The proposed Athena X-ray Observatory, a next-generation X-ray telescope with a collecting area orders of magnitude larger than Chandra or XMM Newton, would, if funded and launched on its current timeline, provide the X-ray spectroscopic sensitivity needed to detect WIM filaments in individual sightlines across the cosmic web, finally turning the WIM from a statistically inferred entity into a directly mapped structure. And crucially, the KIME telescope in Canada and the ASCAP array in Australia are detecting FRBs at rates of hundreds per year, with the total well-localized FRB sample expected to grow to thousands over the coming decade. Each well-localized FRB, one for which the host galaxy can be unambiguously identified, providing a known redshift and therefore a known distance, provides a new, independent weighing of the total electron column density between its source and our telescope. With thousands of such measurements along thousands of independent lines of sight, it will become possible not merely to determine the total baryon fraction in the IGM, but to map its variation with direction, with redshift, and with proximity to cosmic web structures, producing the first three-dimensional map of the WIME's distribution across the observable universe. There is one further complication I want to address before moving to the implications, because it concerns something more fundamental than observational technique. It concerns the interpretation of what we are measuring, and the possibility that even when the baryon census is fully closed, when every atom can be accounted for in one reservoir or another, there remains a deeper question unanswered. That question is not where the baryons are now. It is why the particular balance between galaxies and the intergalactic void is what it is, and whether that balance is robust to changes in the fundamental constants and initial conditions of the universe, or whether it sits on a knife edge that required a specific and perhaps improbable tuning to produce the cosmic environment that made our existence possible. The star formation efficiency of the universe, approximately 5 to 10% of available baryons converted into stars, is not a random number drawn from a uniform distribution. It is the outcome of a competition between gravity, which seeks to collapse baryons into dense, star-forming structures, and feedback, which heats and disperses them. The specific efficiency we observe is the equilibrium point of that competition, set by the masses of stars and black holes, the energy output of supernovae and AGN, the cooling properties of gas, and the depth of dark matter potential wells. Change any of those inputs appreciably, make black holes more massive, or supernovae more energetic, or dark matter halos shallower, and the equilibrium shifts. Make the feedback too efficient, and almost no baryons condense into stars. The universe remains dark. Make it too inefficient, and almost all baryons condense rapidly into the first generation of stars in the first billion years. The universe exhausts its stellar fuel supply before the conditions for complex, heavy element chemistry are established. The 5 to 10% efficiency we observe is precisely the range that allows stars to keep forming continuously over cosmic timescales, slowly enough to last 13.8 billion years, efficiently enough to have produced the stellar generations needed to build up the carbon, oxygen, nitrogen, iron, and silicate minerals from which planets and biospheres are composed. Whether this is a coincidence, a necessary consequence of the physics, or evidence of some deeper anthropic constraint on the conditions in which observers can exist, that question sits at the intersection of astrophysics, philosophy, and the limits of what any science can ultimately explain. What we can say with confidence is this: the emptiness of galaxies is not a failure. It is a feature. It is the direct consequence of the physical processes. The supernovae, the AGN winds, the reionization, the large-scale shock heating that made the universe a place where stars can keep forming, where heavy elements can keep accumulating, where planetary systems can keep emerging over the billions of years it takes for chemistry to build minds capable of asking why the galaxies are empty. The emptiness is the cost of the stability. The missing baryons, floating in the invisible warmth of the WIM, are the price paid for the longevity of the stellar universe. Stand at the edge of what we know and look outward. Not toward the stars, There are not as many of them as you might think, relative to the total, and they are not the story, but toward the vast, tenuous, luminescent nothing of the warm intergalactic medium, the WIM, the invisible ocean in which 3/4 of all ordinary matter drifts at temperatures between 100,000 and 10 million degrees, too hot to form stars, too thin to emit visible light, too vast to have been mapped by any instrument we have yet built. What does the next decade of observation need to accomplish? What questions, precisely, need to be answered before the missing baryon problem transitions from a partially solved mystery into a fully characterized chapter of cosmological science? The first priority is completing the three-dimensional census. The FRB-based measurement of 76% of baryons in the IGM is a global average. It tells us the total fraction integrated over all lines of sight and all cosmic epochs accessible to the current FRB sample. What it does not yet tell us is how the baryon fraction varies across the cosmic web. Whether the filaments are baryon-rich compared to the voids, how the density of the WIM changes as you move from the cores of galaxy clusters outward into the field, how it evolves with redshift as the feedback history of the universe unfolds over cosmic time. The 1,000 FRB dataset that should exist within this decade will begin to answer these questions, providing a first statistical map of IWIM density variations across different large-scale structure environments. The second priority is the direct detection of individual IM filaments with multiple independent techniques. The Athena X-ray Observatory, if it proceeds toward its target launch date, provide the X-ray spectroscopic capability needed to detect OVI and OV reabsorption in dozens to hundreds of individual filaments, building a statistically robust sample of direct WIM detections that would allow the measurement of not just its total mass, but its chemical composition, thermal state, turbulence level, and spatial distribution. The chemical composition is particularly important. The heavy elements, carbon, oxygen, silicon, iron, that are present in the WIM were not produced in the Big Bang. They were synthesized in stars and ejected by supernovae and AGN winds. Their abundance in the WIM is therefore a direct tracer of the history of feedback, a chemical record of every starburst and quasar eruption that has occurred over cosmic time, preserved in the warm gas between the galaxies. Reading that record would give us a detailed history of how and when the baryon cycle operated, which is currently one of the most uncertain aspects of our understanding of galaxy evolution. The third priority concerns the circumgalactic medium, that 15% of the baryon budget residing in the extended halos surrounding galaxies, and its role in the ongoing baryon cycle. Current observations with the Cosmic Origin Spectrograph have revealed the CGM to be an extraordinary environment, turbulent, multiphase, chemically enriched, with gas moving both inward toward the galaxy and outward into the IGM in the same system simultaneously. But most CGM observations sample the gas in absorption against background quasars, a one-dimensional probe that cannot reconstruct the three-dimensional space distribution and kinematics of the gas. The next generation of large-format integral field spectrographs on extremely large telescopes. The Extremely Large Telescope, currently under construction in Chile and planned for first light in the late 2020s, will carry instruments capable of mapping the CGM in emission across extended regions around nearby galaxies, providing the spatial context currently missing from quasar absorption line studies. Fourth priority, and in some ways the most philosophically loaded, is the redshift evolution of the WIM and the baryon fraction in galaxies across cosmic time. We know the present-day distribution. We know, from cosmological simulations, what the distribution is predicted to have been at high redshift. We do not yet have the observational capability to measure the baryon fractions of the IGM, CGM, and galaxies simultaneously at redshifts above 1. In the epoch when the cosmic star formation rate and AGN activity were at their peak, when the feedback processes that shaped the present-day baryon distribution were most energetically active. Bridging this gap requires both the FRB sample. High redshift FRBs are beginning to be detected, with the record holder in the 2025 Connor et al. Sample sitting at a redshift of 1.5, corresponding to a look-back time of approximately 1 billion years, and the next generation of X-ray and ultraviolet space observatories capable of measuring WIM absorption at cosmological distances. The fifth priority brings us back to the beginning, to the question with which this entire story began. We now know where most of the baryons are. We do not yet fully understand why they are there in the precise form and distribution that we observe, rather than some other configuration that the same physics could in principle have produced. The detailed numerical simulations, Illustris TNG, Eagle, Simba, Flamingo, have made enormous progress in reproducing the observed galaxy population and the broad properties of the cosmic baryon distribution, demonstrating that the feedback prescriptions implemented in these models are approximately correct. But the subgrid physics of feedback, the way supernovae inject energy and momentum into the interstellar medium, the way AGN jets interact with the surrounding gas, the way cold streams of cosmic web gas penetrate hot circumgalactic halos, is still implemented in these simulations through parametrized prescriptions tuned to match observations rather than derived from first principles. The underlying physics of feedback, at the microscopic level, is still being worked out, and the degree to which the present-day baryon distribution is robustly predicted by those underlying physics, rather than being a tunable outcome of uncertain prescriptions, is not yet established. The next Rubin Observatory Legacy Survey of Space and Time, LSST, will deliver photometric data on approximately 37 billion galaxies over its 10-year survey, providing the largest map of galaxy large-scale structure ever assembled and the most precise statistical measurements of the cosmic web's properties. When combined with the spectroscopic redshift surveys being conducted by DESI, the Dark Energy Spectroscopic Instrument, which has already measured the spectra of more than 50 million galaxies in its first 2 years of operation. This dataset will allow the construction of the most detailed three-dimensional map of the cosmic web in history, one that can be compared point by point with both cosmological simulations and direct WIM detection maps from the FRB archive. The convergence of these datasets, FRBs mapping the electron density, X-ray spectroscopy detecting the WIM directly, large-scale structure surveys mapping the cosmic web, and next-generation X-ray observatories quantifying the feedback history written in WIM metal abundances, represents the program of observational work that will, within the next 2 decades, either confirm our current picture of the baryon cycle as essentially correct, or reveal that something important is still missing. And there is, I think, a genuine possibility that something important is still missing. Not a dramatic overthrow of the current framework, but a refinement, perhaps in the nature of the feedback, perhaps in the physics of the CGM-IGM boundary, perhaps in the early universe observations emerging from JWST that suggest the first galaxies were more efficient and more extreme than we predicted. The JWST results are still being interpreted, and the community has not yet reached consensus on whether the apparently overmassive early galaxies represent a genuine challenge to lambda CDM or are an artifact of systematic uncertainties in stellar mass estimation. But the possibility that they represent something real, a brief epoch of extreme star formation efficiency that preceded the establishment of the feedback-regulated cycle we observe today, is not being dismissed. What those early galaxies would imply, if the overmassive interpretation is correct, is that the baryon cycle had a beginning, a brief, violent epoch in the first billion years when feedback had not yet established itself as the dominant regulator of star formation, when galaxies consumed their baryons at extraordinary rates before the first supermassive black holes grew massive enough to quench them. The transition from that early, efficient phase to the regulated, feedback-dominated phase we observe at lower redshifts is precisely the transition we need to observe across the cosmic history accessible to JWST and the coming generation of infrared observatories. And embedded within that transition is the answer to a question that the missing baryon problem has always been pointing toward, even if it was not always articulated in those terms. Not where did the baryons go, but when and why, and what it meant for everything that came after. There is a number I keep returning to. 1 atom per cubic metre, that is the average density of matter in the intergalactic medium, in the warm, tenuous, nearly invisible ocean that holds 3/4 of all the ordinary matter the universe has ever made. 1 atom per cubic metre, a volume of space equivalent to a large wardrobe, a generous bathroom, the interior of a small car. 1 atom drifting alone in that space, at a temperature of millions of degrees, moving at hundreds of kilometres per second, and yet so isolated from any neighbour that for all practical purposes it has never interacted with another atom in billions of years. We are made of atoms that were once in stars. Those stars formed from gas that once drifted in the intergalactic medium. That gas was expelled from earlier galaxies by winds driven by supernovae, whose progenitor stars formed from gas expelled from still earlier galaxies in an unbroken chain of recycling and redistribution that stretches back to the first few hundred million years after the Big Bang. Every carbon atom in your body, every oxygen molecule in your lungs, every iron atom in your hemoglobin was once part of that warm, invisible ocean between the galaxies, floating at a density of 1 atom per cubic metre before gravity found it and drew it back into a gas cloud and a protostellar disk, and a stellar wind, and a supernova remnant and an interstellar cloud. And eventually, you, the emptiness of galaxies in this light, is not emptiness at all. It is the universe's working memory, the reservoir of matter. It is still processing, still cycling, still deciding what to do with. The WIM is not a graveyard of baryons that failed to become stars. It is a waiting room. Matter cycles in and out of it on timescales of billions of years, expelled from galaxies by feedback, cooling back in through cosmic web filaments, accreted again, processed, expelled again. The present-day distribution, 76% intergalactic and 24% galactic, is not a final state. It is a snapshot of an ongoing negotiation between gravity and thermodynamics that has been running for 8 billion years, and will continue for billions more. What I find most extraordinary about this, and I say this having spent a considerable amount of time sitting with the numbers, is that the answer to where the matter went turns out to also be the answer to why anything exists at all. If the universe had been slightly different, if the feedback from black holes and supernovae had been slightly less efficient or slightly more efficient, or had operated on different timescales, then the 5 to 10% of baryons that ended up in stars would have been a different number, and a different number means a different stellar population. A different stellar population means different nucleosynthesis, different heavy element abundances, different planetary chemistry, and possibly no pathway to the particular molecular complexity that underlies life as we know it. The missing baryons are not a problem to be solved and filed away. They are a clue to the calibration of the universe. Their distribution, their temperature, their location, their chemical composition, their ongoing exchange with the galaxies at the nodes of the cosmic web, encodes the history of every feedback event that has ever occurred in every galaxy across all of cosmic time. Reading that record completely is one of the defining scientific projects of the coming century. Vera Rubin, standing at her spectrograph on a cold mountaintop in the 1970s, did not know she was measuring the first unambiguous evidence that the universe's matter budget was wrong. She was trying to understand how galaxies rotated. She found something that changed cosmology. She was told repeatedly that she did not belong in the rooms where the questions were being asked. She asked them anyway, and the questions she asked, about the mass that was missing, about the darkness that outweighed the light, about the gap between what the universe contained and what we could see, cascaded forward across 5 decades into the FRB surveys and the X-ray observatories and the Sunyaev-Zeldovich maps and the 2025 result that finally weighed the invisible ocean and found the missing 3/4. That is how science works, at its best. Not as a series of individual revelations, but as a relay, each generation carrying the question a little further, handing it to the next with more precision and more depth than it had before. Rubin handed the mass discrepancy to the theorists of the WIM. The WIM theorists handed it to the X-ray astronomers. The X-ray astronomers handed it to the FRB community. The FRB community handed back an answer, and then, in the same breath, revealed that the answer is not quite complete, that the baryonic cycle is still not fully mapped, that the early universe holds surprises that the current framework does not yet fully explain. Science does not give us endings. It gives us better questions, and perhaps that is precisely as it should be, because a universe fully explained is a universe that no longer surprises us, and a universe that no longer surprises us is not the one we actually live in. We live in one that hides 3/4 of its own matter, in a form we could not detect until someone thought to use the light of a distant explosion as a flashlight and hold it up to the void. We live in a universe where the emptiness turns out to contain most of everything, where the nothing is, on closer inspection, the whole point. The matter was never missing. We were missing it, and somewhere in that vast warm ocean between the galaxies, in the filaments we are only now learning to read, the rest of the story is waiting to be found.